Robin Byrne, Associate Professor of Astronomy at Northeast State Community College in Blumpville, Tennessee. Behind the camera is Adam Thanz, Planetarium Director at Bays Mountain Park and Planetarium in Kingsport, Tennessee. You'll be hearing him make some commentary as we work our way through walking to the center of the Milky Way. Now on this walk that we're doing, we have scaled down our entire galaxy, where 1 foot is a little under 5 light years in length. And we are starting at our solar system and we're walking to the center of the galaxy. So we're covering about 1/4 of our galaxy. Along the way, we're going to stop at various objects that are found within not just our galaxy, but types of objects found in other galaxies as well, and get a sense of the sizes of various things and the distances of things within our galaxy. Now we are starting at our solar system. And so here is our solar system. Now you might think that this circle is the orbit of Pluto, and you would be wrong. That little dot in the center, which is actually drawn too large, represents the sun and everything out to Pluto. This outer circle is the outer reaches of our solar system, a region called the Oort cloud, which extends well beyond the sun. And this is a reservoir of comets that can be what are called the long period comets that come around once every few hundreds to thousands of years come from this region. So this is kind of the extent of our sun's gravitational pull is out to here. But everything we actually think of as our solar system is in that teeny tiny dot. So our solar system, that means the sun and everything that orbits around our sun, the planets, the asteroids, the comets. As of 2013, so this is old information, there are 696 confirmed stars with planets. I think now it's well over 2,000 stars that are confirmed with planets. There are as many to 4 to 8 billion stars that are thought to have planets just within the Milky Way galaxy. And then, of course, there are billions of other galaxies. So there are probably a whole lot of planets out there that we do not know about. On our scale, the next nearest star would be a foot away from here, and we would not be able to see it. It would be too tiny to see, just as our sun would be too tiny to see in this illustration. Now the next object we're going to travel to is the Pleiades star cluster, and let me check my steps here. Oops, I know why. And that is going to be 42 steps from here. So we have reached the Pleiades. Now on this scale, these things, the Pleiades would be about this big across. So give you a sense of size. Now it's obviously not just in a line, but wasn't going to waste paper and make a whole big circle. So that's how big across the Pleiades is. Organize my papers here. Here's a image of what the Pleiades looks like. It's a star cluster. This is called an open cluster. That means that over time, these stars will drift apart. So that gives you a sense of what we're talking about here. Pleiades is also known as the Seven Sisters. It is a cluster of approximately 1,000 mostly high mass stars. It is one of the closest open clusters to the solar system. The stars all formed out of the same cloud of gas and dust at approximately the same time, about 100 million years ago. Because it's an open cluster, the stars will eventually drift apart. It is estimated that this will occur in about 250 million years, so we're not going to see it. In Japanese, the Pleiades are called Subaru, and it is used as the logo for the car company. There are 1,100 known open clusters in our galaxy, but many more are thought to exist. So we visited the Pleiades. Up next is going to be the Orion Nebula. We've done 42 steps so far. Orion is 137 steps from the solar system, so we'll start as our first step is number 43 and work our way up to 137.
Here we are walking towards the Orion Nebula, which is one of the highlights of the winter sky. You can see the Orion Nebula with just your eyes as a small diffuse gassy area and right in the middle of the sword of Orion. The sword is just below the famous belt of Orion, which is made of 3 bright stars in almost an exact line, but you can see that. Binoculars of course show more, and a telescope really shows it well.
Alright, we are at the Orion Nebula, and like the Pleiades, I've got a strip of paper representing its size. So now we're getting bigger than the Pleiades, much bigger than the solar system. And let me dispatch with my paper here. Pull out my interesting facts. So here's an image. These are black and white because I have a black and white printer of the Orion Nebula. It's a beautiful object through telescope, and good through binoculars too. We're 1,300 light years from the sun at this point. The center star in the sword of the constellation of Orion, this H2 region, is the location of star formation. The heat from newly formed stars causes the gas cloud to glow. This is the closest star-forming region to our solar system, and the first to be discovered, and it was discovered by Galileo. Of course it was. Hubble images show disks of material around the forming stars. It is hypothesized that planets will form in these disks. The total amount of gas and dust in the nebula could make approximately 2,000 stars the size of our sun, though the cloud will dissipate before all of it is used to make stars. There are likely thousands of these regions in our galaxy. So we saw the Pleiades, which is basically a new group of stars formed out of a cloud like this. So this is going back a step in the life cycle of stars, where here stars are just starting to form. So we are currently 137 steps from the sun. Our next object is the Ring Nebula at 242 steps from the sun. So we've got another 105 steps to go.
Yes, we're off to the Ring Nebula. The Orion Nebula, I didn't really get to finish, but it is really great to see in a pair of binoculars or a telescope. You don't have to have a telescope to see it though. And it is a star-forming region. It's they're called stellar nurseries because that's where stars are born. Now, not all stars for the whole galaxy, but if there's a region of dust and gas, it will collapse under its own gravity. It will form new stars there and eventually be a cluster of stars. So, like the Pleiades, where we started, that's a relatively young cluster of stars that formed out of a past nebulous region. Stars have a life. They're not living things like us, but they do have a life, and eventually they will die, and you'll learn an example right now.
So the Ring Nebula is an example of a star that has died. So in this case, much smaller than the other objects comparable to our solar system in size. This outer edge, it represents the size of the Ring Nebula. And the interstellar winds are picking things up here. Here's an image of the actual Ring Nebula. So the circle I drew is this outer circle. And you might be able to see a tiny little dot in the center there, which is not showing up on the camera, or is showing up. So that's a white dwarf at the center of this nebula. This is considered a planetary nebula. Early astronomers looking at these objects through their telescopes thought they looked like planets, which is how they got their name, basically because of the round size. In reality, they are formed when a low-mass star nears the end of its life. The red giant star puffs off its outer layers of gas, exposing the carbon core. The heat from the core causes the expelled gas to glow. Meanwhile, the core collapses to become a white dwarf. Over time, the gases will continue to move outward away from the white dwarf. As this happens, it will fade, and the gases will get mixed back into the interstellar medium and be used to make a new generation of stars. There are approximately 3,000 known planetary nebulae in our galaxy. There are likely thousands more. We're now going to leave the Ring Nebula to go visit an unusual star called VY Canis Majoris. We've got 272 steps to take to get there.
We recently just heard about the Ring Nebula, a planetary nebula. So I talked about the Orion Nebula, where stars are formed. Talked about then when they form, there'll be actual stars living their lives along what's called the main sequence. Usually they're in clusters. Our sun is actually unusual in that it's by itself. And then eventually they do die. Now it depends on the size of the star as to what happens in its death. For stars like our sun, they don't explode in spectacular supernova. They puff out its outer shell of gases, like Robin described, and create what essentially is like a smoke ring in space. The Ring Nebula is in the constellation of Lyra the Harp. That is a summer object. So, very late spring, we're going to see the summer triangle rise in the east after sunset. One of those stars is Vega. It's the brightest of the three of this triangle. It's also the one that's the most northerly, and it is the brightest star in Lyra the Harp. The Planetary Nebula, Ring Nebula, can be found in that area. It is a telescope object. Even binoculars will not show it, even as a dot. But you will need a telescope, and you'll also need some kind of modest, a good amount of magnification. Not a huge amount, but a modest amount to see the ring. The central star, the white dwarf that Robin pointed out, is the remnant core of that star. So it's just the small middle bit that what's left, and it will die out basically just by heat losing its energy and fade away.
We have reached VY Canis Majoris, that little dot, which is too big. So here is an artist's impression of VY Canis Majoris, and it's showing if our solar system were placed inside of it, the orbit of Saturn would fit inside of this star. So this is a very large star. This is called a red hypergiant. This is one of the largest known stars in our galaxy. From the picture you can see that our solar system out to the orbit of Saturn would fit inside the star. I'm going to wait for the car to go by. If our sun were the size of a balloon 17 inches across, and we replaced it with this star, and we had started at our sun, where we are now standing would be close to the edge of this star. So from where we started walking to here would have been from the center of this star to its outer edge if our sun, in comparison, were about 17 inches across. This star is near the last stage of its life. It began as a high-mass star, and due to the changing forms of fusion in its core, has grown to this enormous size. The outer edges of the star are so far from its center that gravity is very low, so the gases are being blown off over time. There are 11 known red hypergiants in our galaxy alone. So you may have noticed something looks a little different. So let me tell you a story. Prior to filming this, we were also filming a walk through the solar system, where we started at our house and made our way to Pluto. And then when we got to Pluto, we started this video. Guess whose phone's battery died right about here? So it's the next day, but we're still at VY Canis Majoris, and we are about to head out to the Crab Nebula. VY Canis Majoris was 514 steps from the solar system. Crab Nebula, 683. So we have 169 steps to take to get to our next destination. Let's see if we make it today.
Yes, we're on our way to the Crab Nebula, and we'll be learning about basically the death of stars there. We talked about the Planetary Nebula, the Ring Nebula, where smaller stars like our sun, and that's how they will die. But when larger stars die, they don't just puff out their outer shell of gases, they explode. And they don't explode from the center, they actually explode from a shell. So essentially what will happen is the star becomes, when it starts to die, it becomes unstable. The outer envelope of the star will expand greatly, and then it has no more nuclear fusion to keep pushing outwards. And then that envelope of material collapses onto the star under gravity. And it doesn't just scrunch down to a point, it scrunches down to kind of a shell, imagine a small sphere, and about the size of our sun. And when it collapses onto that, it rebounds, but does so in a supernova explosion. It's kind of a simplified version of explaining what happens. So the explosion occurs at a shell out into space, making something we call a supernova remnant, which is the Crab Nebula is one of. The inner part explodes inwards and can create either a neutron star, a pulsar, which is a rotating neutron star, or a black hole. Now let's learn about the Crab Nebula.
All right, I actually walked a little bit further so we wouldn't end up in the middle of the road or next to a loud creek. So we're slightly farther. But Crab Nebula has a size represented by that. So picture, again, a big round circle about that big across. That tells us how big it is. Put that away. And here's an image of the Crab Nebula. So what we are looking at is a supernova remnant. So this is a place where a star has exploded. All of its gases have been blasted out into space, and we get beautiful images like that, even prettier in color. Among our interesting facts, in 1504, Chinese astronomers observed a bright guest star in the sky. It was so bright it was visible during the daytime. That event was a star blowing itself up in a supernova. As it blasted off its outer layers of gas, the gases were heated enough that they are still glowing today. The remaining core of the star collapsed down to become a neutron star, and it was the first neutron star to be discovered. Over time, the gases will continue to travel outward and dissipate and will eventually no longer be visible. The gases are going to get mixed back into the interstellar medium, and they will be used to make the next generation of stars. There are 21 known supernova remnants in our galaxy. So, the Crab Nebula, in terms of light years, is about 6,500 light years from our solar system. So far, we've been traveling in the disk of the Milky Way. Within the disk, there's a lot of interstellar medium, all that gas and dust, and stars blowing up, and it limits how far we can see. We are pretty much at the optical limit within the disk of our galaxy. Now, we can see farther using other wavelengths of light, so infrared, microwaves, radio waves, we can see to the center of the galaxy. But optically, this is about as far as we can look within the disk. So our next destination is something we can still see optically much farther away, but it is outside the disk of our galaxy, in the halo of our galaxy. So our next destination is a globular cluster called M13. And since we are traveling out of the disk of the galaxy, we are traveling a really long distance. Adam gets to banter for a really long time because I've got 1,900 steps to count. So have fun listening to Adam while I have fun counting up to 1,900. All right, I'm going to start counting now.
So we're now in a quiet area. There's a lot of water in our area here. The galaxy. Okay, so we were talking about the death of stars, where the supernova explosion And that material that explodes outwards, the supernova remnant, is the result of a very large star, much bigger than our sun, dying. And it's also the source of heavy elements, things heavier than iron. And so we know that we, all of us, and our Earth, our solar system, are actually from previous stars that have died, because we have elements greater than heavier than iron. Now, in astronomy, you'll learn about, especially in the history of astronomy, how astronomers kept wanting us to be in the middle. The Earth is the center of the solar system. Well, maybe the sun is the center of the galaxy. Well, maybe we're the center of the universe. Well, obviously we're not in any of those things. We're part of it. But another thing that's kind of self-centered is even labeling of types of stars. Our sun is a population 2 star. I'm sorry, a population 1 star. And then old ancient stars are called population 2. Well, turns out they wanted us to be first. It's always that way. We are actually, from a product from past stars. So ideally, ancient stars should be called population 1, but it's the opposite. It's we're number 1 mentality, so we're population 1 stars. At least our sun is. Our galaxy has hundreds of billions of stars. We don't know the exact number. 200 billion to 400 billion is a good estimate. Our galaxy, known as the Milky Way, is a spiral galaxy. It's actually a barred spiral galaxy. It was recently discovered probably about 10-15 years ago, that there's a small bar structure shape in the center of our galaxy. So when we look to other galaxies, some are just pure spiral galaxies. Some of them have a bar structure in the middle. So we're that type. Also because of that, and also of accurate measurements, we know that our galaxy is not like a big round ball like an elliptical galaxy, but kind of flat, not paper thin. Imagine a big kind of pancake in space. There's thickness to it, and that's the disk of our galaxy. Get over for the car. The disk of our galaxy, like I said, is kind of pancake shaped. There is a general bulging thickness in the middle, and there is a general structure that encircles the entire galaxy that is kind of spherical. It's called the halo. So let's look at each of these parts. The disk. That's where our sun is, our solar system is. We are about 2/3 the way out from the center. So we're not in the center of our galaxy. We're about 2/3 the way out. In the summer night sky, basically after sunset in the summertime, we will see low to the south the constellation of Sagittarius. Scorpius is also right next to it. And if you're lucky enough to be in a dark enough place to see the Milky Way with just your eyes, in the summertime, down to the south, down low, you're going to see that the Milky Way is quite bright and has a lot of structure. Binoculars really show this. That's towards the center of our galaxy. And so that's why we see all that structure and all that brightness, because we're looking at a much greater concentration of stars, also a lot more structure of dust and gas that's blocking starlight. So we get this mottled appearance, and it's really just, it's a treat to see in the night sky. So we're about 2/3 the way out. So we're along with the spiral arm structure of our galaxy. Now the spiral arms, why are there spirals? Why isn't it just like a phonograph record, or it's just this big round disc? Well, there's a thing called density waves. And what this is it's actually something very common. It's part of physics. It's also harmonic. And we talked about harmonics with Saturn's rings and the walk through our solar system presentation. But so a good example is a traffic congestion, where you have a traffic jam. It's not where everybody's stopped in the road, but you're driving along the highway, and then all of a sudden all the cars are kind of slowing down, and then you get to the point where everybody's going the slowest, and you look to see, is there an accident somewhere? And there's nothing. And then the cars start getting farther apart from each other. You can start speeding up and then leaving. That's a density wave. And so what's happening is that there's just too many cars on the road at any one particular place, and so this congestion occurs, and you have to kind of drive through it. So there's nothing physical that you're driving through, it's just the congestion that you're having to deal with. If you were in an airplane or a drone up above the highway and saw this, that slowdown of traffic doesn't just sit there at one place on the road. It travels along with the traffic, but not at the same speed. It goes a lot slower. So the cars, they go through, they slow down, and then they speed up and pass on. Well, the density wave, that feature, that effect is called the density wave. In our galaxy, with the spiral arms reveal the effect of a density wave, which is pretty neat. There's dust and gas always in our galaxy. A density wave passes by. The dust and gas then gets jostled about, starts forming new stars, and just behind its wake will leave a whole bunch of newly formed stars. So when you look at a galaxy image, an image of a galaxy, you're going to see a whole bunch of bright stars lining that edge. And so it's part of the process in which our galaxy keeps forming new stars, is this density wave. And then trailing behind, way back, the stars eventually live their life and die. And then there's it looks like nothing, but there really is stuff there in stars, but just not much. And then the next density wave. In the center, and kind of focused very close to the center, is the bulge. And so this is where it kind of is like a little ball. So imagine a big disc, which is what we have been walking through, even though now Robin and I are going up above the disk of our galaxy. In the center is this bulge of stars, a kind of a small ball of stars. And then if you really pulled back away from the galaxy and you could see it from afar, there's also what's called the halo, which is some rogue stars, but also interstellar medium and also dust and gas. It's like a giant ball around the entire galaxy. So it's not just a central bulge area where it's... What was that?
Halfway.
Oh, we are going halfway.
We are halfway right now.
Okay. We just got an alert from our travel agent that we are halfway in our destination. So the halo, it's very thin. There's obviously not much there compared to the disk of the galaxy, but in the halo we can find things like globular clusters, which is where we're going to. And so we're going to globular clusters, in which we're going to be able to see an object that is best described as a globular cluster, to be honest. It's a big collection of stars. They're all very close to each other compared to an open star cluster, like the Pleiades star cluster. But they're not touching. They're still like a light year or more apart from each other. But instead of a few hundred stars, maybe 1,000 or 2,000 stars for an open cluster, globular clusters have usually 10 to 50,000 at the low end stars, going up to 1 million or more stars on the high end. And so when you see them in a telescope or a photograph, you will see. Now we're going to do the crossing of our driveway, or the road here to our driveway. So globular clusters are huge groupings of stars, and they kind of look like cotton balls in space, but they're very cool. And there was some controversy about them, again, about 10-15 years ago, in which astronomers weren't sure what was their cause, where did they come from, how old are they, and we were getting some confusing measurements as to their age. And so astronomers thought that somehow, or a few astronomers I should say, somehow thought, wait, they're older than our galaxy. How can that be? And they were wrong. So that's how science goes. You have an idea, you test it, you realize if it's wrong, you throw it out. So they were wrong. They're almost the same age as our galaxy. And their cause is still not fully understood. Could they be remnants of dwarf galaxies that are still orbiting our galaxy? Could they have formed with our galaxy in the early stages? So it's still kind of up in the air as to their origin. How far now? Robin, how far now?
600 more steps.
All right, uphill. Now our galaxy has all these interesting components within it, which is what we're learning about. The globular clusters, open clusters, planetary nebula, supernova remnants. There's also features that are called diffuse nebula, which the Orion Nebula is like, and also dark nebula, which is really gases that are not emitting light, but acting as silhouettes. They're blocking light. And those always make images very interesting to look at. Now our galaxy, like pretty much every other galaxy, exhibits a feature, called, I'm blanking on it. The rotation of the galaxy itself doesn't have lessening speeds as you go away from the center, but it's consistent as you go out. And that is due to dark matter, in which dark matter, flat rotation curve, that's what I wanted to remember, that going uphill. Dark matter.
Up into the halo.
That's true. We're going up into the halo. So with the dark matter, we can't see it. That's why we call it dark. We don't know exactly really what it is. So again, kind of dark. But we think it's matter because it acts like it, because it has a gravitational signature. So there is mass of some sort spread out through our galaxy that's making it rotate evenly instead of differing speeds as you go away from the center, like our solar system is and how it rotates. And so it's one of the many pieces of evidence for dark matter that's out there. How many more? Robin? She's counting. Leave her alone.
More.
200 more. Okay. So you can see just how far we are traveling to go out of our galaxy to this globular cluster. So I'll also talk about extinction. Not like the dinosaurs, but light extinction, in which when we look out in our galaxy, it's hard for us to see because of all that dust and gas. And so it attenuates the signal. Basically, it just dims and dims farther and farther objects when you're looking through thicker parts of the galaxy. And we can't see really far away. Well, the James Webb Space Telescope that's about to launch is going to help with that, because it looks at the infrared instead of visible light. And guess what? dust doesn't affect infrared light as much as white light. And we're going to see into areas of our galaxy and also out into the reaches of the universe much farther than we have before, because it's going to kind of use a dust filter, so to speak, and allow us to see what has been blocked. There have been other spacecraft that can see infrared, and so we know for a fact a lot about our galaxy. But that new space telescope will help us in learning more.
Oh boy, we have made it to M13. So we took a little breather, caught our breath, had some water, and now we're ready to talk about M13, our globular cluster. So first, we're going to get a sense of how big this thing is. This is a big one.
I'm putting my hands in front of the camera. She's still going. Whoa. Whoa.
Alright, so that's how big across our globular cluster is. You can see this is a nice big object. We talked about the open cluster earlier, much smaller. Globular clusters have a lot more stars in them than open clusters, hence the size. And also because they have so many stars in them, they are held together gravitationally. So the Pleiades, being an open cluster, those stars are going to drift apart. Globular clusters like M13, they are gravitationally bound. They will stay together till they die. Got an image of what M13 looks like telescopically. So that is our cluster of stars. So every star you're seeing there, for the most part, is a member of this cluster. Some of our interesting facts. This cluster has approximately 3,000 stars held together by gravity, which is what gives it a round shape. Unlike an open cluster in which the stars drift apart over time, a globular cluster remains held together. Globular clusters are located in the halo of the Milky Way and are composed of first-generation stars made of only hydrogen and helium. Because there are so few heavy elements present, planets are not expected to exist in these systems. With almost no interstellar medium, no new star formation occurs in the cluster. There are approximately 160 known globular clusters in our galaxy, and estimates are that there are 10 to 20 more. So we have made it almost to the end. Our last location is the center of the Milky Way. Now, to be kind to both you and me, instead of, because we've just traveled out of the disk up to the globular cluster, we're not going to then travel from the globular cluster down to the center. We're going to pretend all of that distance we just covered, we covered within the disk. So we've only got 96 more steps to get to the center of the Milky Way. And I'll pick up our M13 while we go.
And I'll just add a tiny bit about M13. It's in the constellation of Hercules, and Hercules rises in mid-spring in the east, and Hercules is known for its central four stars that make what's called the keystone, because it's a keystone shape. And if you look online anywhere, you're going to find out where M13 is. Well, it is an unaided eye object. Dark skies, nowhere to look. You'll just be able to see it. But if you have a pair of binoculars, you should be able to spot it pretty easily. You saw the picture of M13 that Robin had. It looks like a tiny little snowball, little puffball in space. But it's still pretty cool to see an object like that and how ancient it is.
And we are now at the center of the Milky Way. So we are at what's called Sagittarius A star, and our scale model is our tiny little dot here, which is too big, but that at least gives you a sense that this is a small object in the center of our galaxy. This is a radio image, because remember, we can't optically see to the center of our galaxy, but we can detect radio waves. And so that bright bit right there is Sagittarius A star, and then this is a bunch of gas and dust and stars orbiting around it. So the center of our galaxy has a supermassive black hole, and that's what Sagittarius A star is. This is a very strong radio source located in the center of our galaxy. Observation of star motions in this region indicate that it is very small and extremely massive, which implies it is a supermassive black hole. The mass of Sagittarius A star is estimated to be about 4 million times the mass of our Sun. And its size is smaller than the orbit of Mercury. So think about that, 4 million of our suns crammed inside the orbit of Mercury. So that's a very dense, compact object, which is what a black hole typically is. Supermassive black holes are thought to exist at the centers of all galaxies. While there are several thousand stellar mass black holes in our galaxy, ones that are just the result of a single star dying, this is the only supermassive black hole in the Milky Way. But since there are billions of other galaxies, there are billions of other supermassive black holes. So we have just traveled roughly a mile from the center, or rather from our solar system to the center of our galaxy. That's about 1/4 of the entire galaxy. So our entire galaxy would be about 4 miles across. If we wanted to travel to the next large galaxy, which is the Andromeda galaxy, on this scale we would travel about 45 miles. So not a huge distance. I don't want to walk it. We're not going to count those steps, but it's reasonably close based on the scale. Now we just traveled 25,900 light years. And disregarding the fact that a day has passed, in the time that it actually takes to walk it, about a half hour. Now, light takes 25,900 years to travel the distance that we just traveled. And we did it in half an hour. That means that we were just traveling at about 450 million times the speed of light. So, there's a reason why Adam and I were getting out of breath and hot, because we were really booking it. And that's how we got to the center of the galaxy as fast as we did. So I hope you enjoyed our trip through the Milky Way, and thank you for bearing with us.